Right now, out in a darkness so deep it feels like a thought whispered after midnight, a machine older than you are is still moving, steady, patient, tireless. It has slipped more than 25 billion miles from the warmth of home, farther than any artifact our species has ever made. And here is the part that bends the mind. Even at that relentless pace, it would still need roughly 73,000 years to glide to the nearest star. Tonight we're going to walk past the edge of maps, to places where the legends go quiet. We'll imagine ships kicked forward by chained nuclear dawns, consider cultures so vast they farm the light of entire suns, and ask why the universe might one day run down like a clock. If this kind of gentle drift through the cosmos helps you unwind, you're welcome to subscribe and tap like for Space Historian, so you can find your way back to these night journeys whenever you need them. Now breathe, let the room soften. We begin. Picture yourself barefoot on an endless shore. The tide is black glass. The horizon is everywhere. Many people think our little system ends out at Pluto, a lonely, frost-bitten wanderer. But the true boundary lies much farther, where the sun's breath runs out of strength. That place has a name, the heliopause. It is an invisible frontier about 11 billion miles from the hearth we call Earth, so distant that sunlight itself needs more than 16 hours to make the trip. At motorway speed, without sleep or stopping, you would need around 12 million years to drive there. Think of everything you've ever known as living inside a shimmering bubble, a soap film in the void, blown by the steady outflow from the sun, an airy river of charged particles rushing outwards at more than 1 million miles per hour. That wind presses upon the emptiness and shapes it, curving a shield around our planets like a cupped hand. But even the most faithful breeze fades. At the heliopause, our bright bubble collides with the wild weather of space between stars. Grains and ions from far-flung suns wash against our boundary as surf slaps a seawall. The temperature dives toward the bottom of all thermometers. The character of space itself changes. Here, you have stepped beyond the leash of the only star our kind has ever lived beneath. Voyager 1 crossed that border in 2012, a small, stubborn emissary turning its back on the sun's protection and sailing into the true interstellar dark. Its radio murmurs now need over 21 hours to reach the great dishes that listen for them, longer than a day on your calendar. What the probe sends is quiet, a hush full of measurements and questions, and the cleverest people we have are still learning how to read its meaning. Hold this next truth gently. The frontier that took us 35 years to reach with one of the fastest objects we've ever built covers less than 110,000th of the distance to the nearest star. It's like taking a single step on a journey that would circle Earth 2.5 million times. That's our progress so far. One soft footfall on a road that loops and loops beyond imagining. So the heliopause is not only a line on a map, it's a warning written in frost. Past this edge, the rules rearrange themselves. The sun's warm light no longer matters. The magnetic umbrellas that shelter life from harmful radiation fall away, and time itself begins to act strangely when you move at unreasonable speeds across gulfs where nothing much exists. Standing on that cosmic strand, it becomes plain. Leaving the cradle is not a matter of adding bigger engines or a few clever upgrades. It's a change of kind, not degree. To slip between the stars, we must become a species that can sleep in the cold and wake in the quiet, a people comfortable with long nights and empty rooms. The good news is that our first Pathfinders have already started posting letters home from that darkness. They are our scouts, and we will follow. Imagine now 2 turntables spinning forever in the cold, each holding a memory of us. The records are golden, literally, and on them live whale song and cradle cry, greetings and music from many corners of our world. They ride aboard Voyager 1 and Voyager 2, launched in 1977 with modest ambitions. Tour Jupiter, nod at Saturn, and fade politely into the background. Instead, they accelerated into myth. They are now our earliest star travelers, racing toward constellations they will never reach, carrying messages from a blue world they will never orbit again. Voyager 1 moves at about 38,000 miles per hour, a number that feels like a typo until you imagine it crossing New York to Los Angeles in 4 minutes flat. And yet, after 46 years of sailing, it has barely waded from the shoreline. The nearest close encounter with another star won't come for about 40,000 years. Think of these craft like caravels nosing off medieval docks, bound for coastlines smeared in rumours. The captains knew there might be no return. Still, they carried a world's daydreams with them. The computers on board are laughably small by our pocket standards, yet they keep working in conditions that would crack the bones of ordinary machines. Cold doesn't merely chill up there, it stiffens matter itself. Metals behave like brittle toffee that shatters. Electronics that were faithful for decades begin to fail in peculiar, poetic ways, as if old hearts had learned new missteps. Their power packs, little nuclear hearths, dim year by year. The messengers are dying, but before they go quiet, they are telling us truths we didn't know we needed. They have mapped magnetic fields twisted into arabesques by stellar winds. They have felt the patter of cosmic rays hurled outward by catastrophes that burned long before Earth had skin or sky. Perhaps most humbling of all, they have confirmed that the void is not truly empty. It is filled with a gauze of hydrogen and antique particles, remnants from the universe's childhood. Each day, the signal thins. By sometime in 2025, the voices will probably be gone, their heaters too cold to keep the instruments awake. Then the craft will drift as ghost ships, still moving, always moving, through a night strewn with suns. Their golden records will keep spinning. There is a chance, slim and stately, that in 300 million years an intelligence will pick one up, lower a stylus, and listen. They might hear whale song, laughter, a mother's voice. They might guess that once upon a time, on a small water world that liked to name things, there lived a species reckless enough to throw bottles into a cosmic sea. Yet the greatest lesson Voyager gave us was not just about what lies outside, but about ourselves. It proved we can build tools that endure between stars. The harder question is whether we can last long enough to follow them. Between here and the nearest beacon yawns a darkness so total that the deepest ocean trench feels bright by comparison. Space is not merely empty, it is empty with enthusiasm. If we shrank our solar system so that Earth were a marble in your hand, the nearest star would be a second marble set down roughly 1,400 meters away. Imagine placing one in London and one beyond the far side of Hyde Park, then trying to skim the first so it taps the second. And distance is only the first joke the void plays. In the finest vacuum chambers on Earth, scientists can strip away almost all the air, leaving a thin ghost of particles behind. Millions, in every cubic centimetre. Between the stars, you may find less than a single atom in that same space. Think of trying to swim an ocean whose water is too sparse to feel, whose chill would freeze your blood in a heartbeat, and whose invisible radiation would quietly cook your DNA from the inside out. That is the crossing our ships must attempt, and emptiness is not kind to physics. Sound with no air to ride on simply isn't. Heat has no familiar path to travel, and temperatures hover just above absolute zero. about -450 Fahrenheit, where even helium, the shy element, can freeze. Metals snap like glass. Circuits expire for reasons that read like riddles. The radiation would make Chernobyl look like a spa weekend. Cosmic rays, shrapnel from exploding stars and feasting black holes, hammer through anything at nearly the speed of light. Pack the energy of a fastball into a single subatomic bullet and send it through you. That's what a cosmic ray can be. Enough of those, and cells falter. Minds dim. The journey shortens lives, and the magnetic cocoon that wraps Earth disappears entirely out there. Electric storms stirred by distant suns flicker through the interstellar medium, long slow tempests that could fry unprotected circuitry as surely as a lightning strike. Imagine trying to use your phone in a storm that lasts for centuries. More unsettling still, the vacancy is not even. There are clouds, veils and streams, patches of hydrogen, dust, and the strange mass we call dark matter because we don't yet understand its behavior. Some of these fogs stretch across hundreds of light years. Hit one at a reckless speed and it becomes a wall, and every grain of dust becomes a bullet. Flying between stars at the velocities we daydream about would be like driving into a sandstorm at 200 million miles per hour. You wouldn't feel the bullets, there would be no time to feel them, but your ship would. Even so, in this sparse wilderness we have spotted a lantern that keeps bringing us back to our charts. It burns only 4¼ light years away. You need a telescope to see it at all. Proxima Centauri, a red dwarf the size of a humbled ember, about 1/8 the mass of our Sun, flickers there. If our star is a great bonfire, Proxima is a stubborn candle. The planet that circles in its temperate zone, Proxima b, receives maybe 1% of the light that warms Earth. But the arithmetic of distance changes the story. 4¼ light years is practically next door by galactic standards. At the pace of our quickest probes, the crossing would take those same jaw-dropping 73,000 years. For an immortal species, it would be a long weekend with poor weather. Think of Proxima as a lighthouse you can just make out through fog. Its signal is faint but steady. You know where it is. You can plot a course, but the sea between is cut with storms. The star weighs only about 12% as much as the Sun, yet it throws tantrums that would make our space weather look like a spring shower. In minutes, its flares can release more energy than we humans have used in all our written history. Those flares punish Proxima b, stripping air, flooding ground with radiation, scouring the surface free of easy life. If anything lives there, and perhaps something does, it may have learned to hide deep under rock, or to wear armor that we would envy. Red dwarfs are patient. While our Sun will dim and fail in something like 5 billion years, a number so large it slides off the mind, stars like Proxima can burn for trillions. That makes them compelling destinations for any species with survival in mind. But to reach even the nearest of them is a test unlike any we've faced. Suppose we could move at 10% of light speed, faster than any human-made object has ever moved. The crossing would still take 43 years, a lifetime aboard a ship that is also a village. Children would be born into the mission and grow old under its ceilings, measuring their days by the distant sun ahead. The energy bill for such a push is beyond extravagant. It is mythic. To get a craft the size of the shuttle up to even 1/10 of light speed would demand something like the total energy output of a nation for a century. And if we solved that bill, we would still face the quiet violence of radiation for decade after decade. Still, astronomers are finding rocky worlds around red dwarfs sprinkled all across our neighborhood, dozens within 50 light years. Those ancient, slow-burning suns offer something our own does not. Time in abundance. Time to evolve, to wander, to distribute our risks before our star thins to ash. Proxima is not just a neighbour, it's a policy, a way to ensure we're still telling stories when most lights have gone out. But there is a catch stitched into space-time itself. The universe has a speed limit. We cannot break it by brute force. Einstein showed that nothing with mass can reach the speed of light. As you push harder and harder toward that limit, your mass, as measured by those watching you, appears to climb without bound. To move any amount of stuff at light speed would require all the energy that exists. Not difficult, impossible, carved into the laws of physics like a no-entry sign. Light dashes along at about 671 million miles per hour. At that pace, you could lap the planet 7.5 times in a second, reach the moon in a bit over a second, cross the breadth of our solar system in roughly 11 hours. And yet even light itself needs more than 4 years to carry a greeting from us to Proxima. This limit is the ultimate motorway sign. The punishment for ignoring it is not a fine. It is the unraveling of the arithmetic that keeps reality together. As a ship inches toward light speed, time on board slows relative to clocks elsewhere. At 99% of light speed, a year for the crew might be 7 years for people at home. This is not science fiction. It is baked into the geometry of the universe. The paradox is aching. You could sprint to Proxima and back in what feels like months aboard, only to return to an Earth decades older, with old friends gone and cities grown strange. You would be a traveller stranded in time, and that's before we pay the energy bill. To push a shuttle-mass craft to a mere 1/10 of light speed, remember, drinks down a century of a nation's power. To reach 90%, you would need more energy than the sun makes in 100 years. Even if we somehow found it, the dust between stars becomes ordnance at such speeds. A sand grain hits like a bomb. Sparse gas turns into a sheet of X-rays and gamma, and nothing we can build today could long endure the spray. But Einstein also slipped us a small, careful hope. While nothing can move faster than light through space, space itself can grow and shrink in ways that seem to ignore that limit. The universe has been expanding faster than light could chase since its first moments. If we could learn to persuade space-time to carry us, if we could fold it or swell it behind us and thin it ahead, we might ride the fabric rather than push through it. That idea belongs to technologies so advanced they read like spells. Still, it leaves the door ajar. Our first attempt to cheat the long road doesn't need magic. It wants only the most violent engine we have ever built. Imagine a titanic surfboard and behind it a chain of suns being born, each detonation a kick. Project Orion, first sketched in the late 1950s, proposed a spacecraft driven by the rhythm of nuclear explosions. You toss a bomb out the back, you let it go off, your great steel plate absorbs the blow, and you lurch forward. Wait a heartbeat, throw another, boom, again, boom, again. The figures are frightening and strangely beautiful. Nuclear blasts offer the highest energy per kilogram of any reaction we can plausibly harness. A single fission device stores enough power to keep a great city lit for weeks. Do it not once but thousands of times, and a ship the mass of a small building could be shoved to 5% of light speed, enough to make Proxima a less-than-century voyage. Picture the craft. An enormous pusher plate at the stern, a forest of shock absorbers like cathedral columns, and up front, tucked behind layers of shielding, a habitat. It would be the ultimate motorcycle, fueled not by petrol, but by captured starfire, each pulse a hammer blow. The mathematics behaves. The materials, some at least, exist. The original plans called for armor thick with lead to soak up radiation from each blast. The ride would be brutal. Short, crushing jolts followed by quiet coasts, like living inside a bell that is struck again and again by a giant's hand. And the problems would be serious. Each explosion showers the craft with gamma rays, neutrons, and particles hot with radioactivity. Even with meters of shielding, the crew would take doses their doctors would hate. The vehicle itself would soak up contamination until approaching it without heavy protection would be a mistake no one makes twice. Later refinements swap fission for fusion, trading the dirty scars of split atoms for the cleaner light of joined ones. Thermonuclear pulses, little H-bombs blooming into brief suns, could, in theory, drive the ship faster, perhaps to 10% of light speed, while cutting the radiation the crew must endure. Fusion promises better exhaust, kinder waste, but the engineering climbs to absurd heights. The pusher plate must shrug off temperatures of millions of degrees and pressures stronger than Earth's core. Shock absorbers the size of towers must thump and breathe thousands of times without failing. The magazine, because yes, you must store the fuel, would be a vault of carefully tended miniature stars, thousands upon thousands of them. And yet, simulations behave. The physics sits there, patient, almost inviting. Nuclear pulse propulsion does not require theoretical particles or new laws. It asks for audacity and engineering. Set aside the cost, gather the will, and something like Orion could be built within the span of a couple of generations. The most stubborn obstacle is not a law of nature. It is a law we wrote ourselves. The barrier is not the maths. It is not the steel. It is not the heat, it's political. Building a ship driven by nuclear fire would take a treaty of trust larger than any the world has ever signed. You'd be asking nations to help assemble a vessel that is, in essence, a travelling stockpile of star-bright warheads, a moving arsenal whose unleashed fury could scar a planet. And yet, if we truly mean to reach the far beacons, perhaps we have to learn to ride the tiger without being swallowed by it. Still, there is a quieter way, one that doesn't roar but glides. It borrows not from bombs, but from the universe's own breath. Across the emptiness, an unseen river runs, pure momentum poured out as light. Every photon carries a nudge. When it strikes a surface, it presses, softly as mist, steady as snowfall. On Earth, that pressure is feeble beyond belief, like the weight of a paperclip spread over a football field. But out where there is no air to fight, and no friction to steal motion, even the gentlest, most patient push can grow into speed. Think of tapping a boat with a single fingertip, again and again, on a glass-still lake. Give it enough taps, and it will drift beyond the dock, beyond the cove, beyond the horizon. Solar sails flip our intuition on its head. A sailboat gathers wind to move through water. A light sailor gathers starlight to slip through space. The sail must be gossamer, thinner than a soap film, lighter than a moth's wing, yet strong enough to hold its shape while the sky itself leans upon it. Picture a sheet so delicate you could tear it with a sigh, wrapped around a craft that intends to cross worlds. This is not a metaphor locked to a blackboard. It has flown. Japan's Icaros unfurled a broad, shining kite in 2010 and steered by sunlight alone, proving in the most elegant way possible that photons can be harnessed as wind. Here is why this matters. Sails don't burn anything. They sip from the cosmos and never run dry. Chemical rockets spend their flame in minutes and then coast. Nuclear engines require heart weights of dangerous fuel. But a sail, once open to the star, keeps gathering momentum hour after hour, month after month, deepening its glide until it outruns any firework we've ever lit. If your nights are brightened by these cosmic lullabies, drift with us a while longer. And if you like returning to them, subscribe and tap like for Space Historian so this gentle voyage is easy to find again. Now imagine turning the sky's whisper into a shout. A group called Breakthrough Starshot sketches a plan to swap sunlight for lasers. A vast array on Earth, lacing the night with a tight beam that presses upon sails no bigger than a postage stamp. The payloads, starships scarcely heavier than a paperclip, would feel a hurricane of light for 2 short minutes, leap to a fifth of light speed, and then coast into interstellar dusk. At that pace, something like 134 million miles an hour, tiny scouts could streak to Proxima Centauri in a handful of decades, flash photos of any waiting worlds, and send them home as slender packets of radio snow. The long trek that would take a Voyager tens of millennia becomes a human lifetime of waiting and wondering. But scaling a dream is its own trial. A sail for people is not a handkerchief, it is a country. Hundreds of miles across, spiderweb thin, it would need to hold its poise while being shoved by rivers of light. Keep tension, resist tearing, survive dust strikes like invisible hail, and if driven by lasers, it must drink fire without burning. Most materials would vaporize in a blink under such a beam, so researchers reach for metamaterials. Engineered lattices that bend light in uncanny ways, mirrors that barely warm while they are hammered by brilliance. If we can weave those into sails, the stars come a tiny step closer. Yet sailing is only one kind of grace. Another says, don't carry the pantry, eat as you go. Close your eyes and picture a blue whale in a dark ocean, cruising with its mouth open, sieving plankton by the ton. Now trade seawater for space and plankton for hydrogen. The Bussard ramjet, first imagined in 1960, turns the void itself into fuel. Instead of hauling tanks, the craft spreads an enormous magnetic net, fields the size of worlds, to sweep up lone hydrogen atoms that haunt the interstellar dark. Those atoms are squeezed, heated and fused. Their mass is turned into energy, and that energy shoves the ship forward. It is flight by grazing, travel by harvest. Space is not truly empty. On average, there's roughly an atom of hydrogen per cubic centimetre between the stars. Almost nothing, a ghost of a ghost. But almost nothing multiplied by enormous speeds and enormous nets becomes enough. At a tenth of light speed, a ramjet would collect billions upon billions of atoms every second, a steady stream of fuel from the night itself. Jet engines on Earth gulp air, mix in kerosene, and burn. A fusion ramjet would gulp hydrogen, smash it into helium, and ride the released light. The faster you go, the more you scoop. The more you scoop, the faster you can go. A feedback loop of hunger and haste. Of course, the net, those magnetic fields, must be vast and precise, big enough to catch single atoms at relativistic speeds, gentle enough to shepherd them into a fusion throat without waste. Engineers compare it to catching raindrops with a net while perched on a motorcycle, tearing along at 200 miles an hour. Doable in cartoons, diabolical in steel. And then there's the furnace at the heart, a fusion core simmering at 100 million degrees, 6 times hotter than the sun's center. At that heat, protons slip through their mutual dislike and become helium, giving up energy as dictated by EOMC2. The promise is breathtaking. No soot, no long-lived radioactive waste, just helium and light. But the ramjet hides a riddle with teeth. To harvest enough fuel, you must already be moving very, very fast. How do you reach that speed without the very system you're relying on? It's the cosmic push-start problem. The car can roar once it's rolling, but someone still has to shove. Worse, as your speed climbs, the very hydrogen you swallow becomes hazardous. At fractions like 20% of light speed, incoming atoms smack into the ship, carrying such energy that they behave more like radiation than food, loading your scoop with drag instead of thrust. The craft begins to choke on its own diet, slowed by the very medium it is meant to eat. Newer sketches attempt a clever cheat, use the same magnetic architecture to reshape the local environment, compressing space in front just enough to thicken the hydrogen you want, while smoothing relativity's sharp edges so those atoms don't slam into you as deadly rays. The craft would surf inside a magnetic cocoon, a pressure bubble, where fuel is denser, hazards are tamed, and momentum translates more cleanly into speed. If such a thing could be built, a ramjet would become the pinnacle of living off the land, an ark that feeds as it flies, carrying human stories between suns without ever needing to refuel. And then there is the wildest idea of all, the one that doesn't ask us to move quickly so much as to make the road itself do the moving. A Mexican physicist, Miguel Alcubierre, peered into Einstein's equations and found something that feels like sleight of hand done by the universe itself. The speed limit, no mass can outrun light, applies to motion through space. But space is not a static stage. It can stretch and shrink. If you could compress the fabric of space ahead of you and inflate it behind you, you would ride a wave. Your ship would sit still inside a pocket while the pocket itself is carried forward faster than light. You wouldn't be sprinting. The treadmill beneath your feet would simply run at a furious pace. Think of those moving walkways at airports. Your steps are ordinary, but the belt adds its own motion and carries you swiftly along. In an Alcubierre drive, the belt is a bubble of warped space-time. Inside it, no acceleration bruises the crew, no intense time dilation steals years from their lives, and the usual relativistic shrapnel that batters fast ships never arrives. A hop to Proxima could become a trip of days instead of decades. A pilgrimage to the galaxy's far side could fit inside a human lifetime, with years, not millennia, passing for those at home. The mathematics on paper behaves. Einstein's field equations do not forbid regions where space contracts here and stretches there, even such that, measured from afar, the overall effect outruns light. In the first breaths after the Big Bang, the universe itself blew up faster than light could cross it. Inflation is baked into the story of everything. Alcubierre's craft would be a small, deliberate echo of that ancient hurry, local, tamed, directed. But then the bill arrives. To coax space to do such gymnastics, you don't pay with chemical fuel or even fusion. You pay with something stranger than science fiction. The original estimates call for negative energy on a planetary scale. Exotic matter with properties that look upside down compared to anything in your kitchen. It would need less than nothing for energy density, a kind of anti-gravity that pushes rather than pulls, bending space the wrong way. We have hints of negative energy in quantum physics. The Casimir effect whispers of it, but nothing like the concentrated, controllable stuff needed to wrap a ship and surf the void. To build a starship the size of a famous TV vessel and warp it as proposed would demand an energy budget comparable to converting a gas giant into pure energy. Our sun, shining for 10 billion years, would look thrifty by comparison, and there's a darker wrinkle. Calculations suggest the bubble might act as a broom, sweeping up energetic particles and high-frequency radiation during the trip. When the drive switches off, that built-up fury could be unleashed in a flash, a beam that sterilizes the destination like a cosmic blowtorch. Not the welcome any new star system deserves. Even so, researchers keep nibbling at the edges, working on teensy warp bubbles, looking for measurable distortions of space-time in particle labs, refining the geometry so the energy bill shrinks from impossible to merely outrageous. Some imagine a future where an ancient civilization has laid down a network of warp highways, a stitched-together web of bubbles you can hop between, like cosmic subway stops, crossing light years in the time it takes to sip a cup of tea. For now, though, Alcubierre's drive rests in the sweet country between math and dream. Beautiful, internally consistent, and waiting for a physics we do not yet know. So perhaps we must set aside speed and embrace patience. If reaching the next light in a hurry proves stubbornly out of reach, we can change the question. Not how fast can we go, but how surely can we arrive? Picture a city that never docks. Tunnels and parks, schools and cathedrals, rooftop farms under arcs of glass, families and festivals, and old men telling stories in soft gravity dusk. A generation ship is less a vehicle than a world, a hollowed mountain turned inside out, or a stitched-together flotilla the length of counties, carrying tens of thousands of people on a voyage that will take centuries or millennia. The first passengers will die never seeing the destination. Their children will grow old, knowing only sky made of metal and seasons made of light schedules. Their grandchildren may not remember why their grandparents left, only that the ship is home and the ship keeps going. Such a vessel must be circular in its economy. Every atom recaptured, every breath recycled, water swinging through pipes, steam, rain, roots, and back again. Waste turned to soil, turned to food, turned to song. The engineering is a stack of infinities. Machines designed to outlast empires. Social systems curated to endure longer than civilizations have yet survived. Consider scale. To house 100,000 souls in comfort and redundancy, you might build something dozens of miles long and miles across, with spinning rims that give a credible imitation of gravity at their edges, while the hubs float in calm for factories and algae fields. Power from reactors that sip fuel like monks, gardens under frozen light, libraries holding the whole of Earth's memory. Noah's Ark, not as a boat, but as a borough. The challenges of mind may dwarf the metallurgy. How do you teach meaning that spans 500 years? How do you cultivate duty in a child whose great-great-grandchild will complete the work? History tells us that isolated communities drift. Language splits like branches. Rituals braid into new forms. A minimum viable population for genetic health might be 10,000. For cultural resilience, perhaps many times that, with guilds and arts and redundancy in stories, so no one theme dominates and petrifies. Governance must be supple but steady. The Roman state barely reached 1,000 years. Pharaonic Egypt 3. A ship to Proxima at our present pace might need social glue that holds for 100,000. How do you renew hope when the only landscape you know is corridor and dome, and the only sunrise you've seen is the sweep of lamps cycling on? Some designs spin like prayer wheels, building artificial gravity from motion, with farms along the outward curve, and a zero-G spine where heavy work happens without weight. Life in such halls would tune the senses to slow rhythms. The creak and hush of air systems, the faint tug at your feet when you stroll the outer decks, the yearly festivals that mark another small ring carved on the great calendar of the voyage. And always the archives, seeds and spores in vaults, a freezer of genomes, museums of remembered Earth, rainforest hum bottled and saved, ocean surf trapped in sound, the smell of pine. But even a city with patience might wish for a shorter night between suns. What if, instead of shepherding whole societies through centuries, we could sleep? Not the nightly kind, but a deeper quiet, a pause button on life itself. Imagine this: You close your eyes to the old familiar sky and open them to a new star. Cryosleep, cryopreservation, suspended animation, different names for the same audacious hope. Lower the body's heat, trade blood for protective solutions. Let chemistry slow until the tick of metabolism is almost silent. Where a month passes for those awake, only days or hours would pass for you. You step into a coffin of glass and light, and later, years later, you step out, stealing time back from time itself. Pieces of this are real already. Tardigrades, tiny, stubborn creatures, have shrugged off years of dryness and cold and come back to clamber about as if nothing happened. Certain mammals can be cooled to near freezing and revived. Human organs nap in cold storage for hours while surgeons prepare their new homes. Hibernation is a poem biology already knows how to recite. Cryosleep is the epic version. Push it further. Add chemistry to stop ice from shredding cells, calm the panic of proteins as they cool, and hold the brain in a glass-like stasis where memory's patterns wait without fading. But this is not a gentle piano piece. Ice is vicious at small scales. Crystals grow like knives, slicing membranes, rupturing vessels, scattering the architecture that makes you you. To dodge those blades, cryonic protocols replace blood with cryoprotectants, antifreeze molecules that keep water from crystallizing and instead guide it into a smooth, vitrified state. Done perfectly, cells become glass, not gravel. Even then, revival is a choreography of seconds and gradients. Warm too quickly, and cracks race through tissue. Warm too slowly, and chemistry fails to restart in the correct order. Hearts must find their beat. Lungs must remember to unfurl. And most delicate of all, the brain's sea of synapses, trillions of tiny bridges, must wake in the same arrangement it had when the lights went out, with the same stories attached to the same names. Some dream of hiring machines we have not yet built to help with this. Medical nanobots patrolling capillaries like gardeners, mending torn proteins, patching membranes, tidying the microscopic shrapnel left by cold. Others suggest a middle path. Don't freeze completely. Induce a controlled torpor, a near hibernation, using drugs and targeted cooling so the voyage shrinks from intolerable to bearable. Sleep for months or a year. Wake for a season to work and socialize, then sleep again. A hopscotch across time instead of a single long leap. Yet the heaviest weight may be psychological. To you, the journey becomes a blink. To those who kiss you goodnight before you go under, it becomes a life. You would open your eyes to a future where everyone you loved has finished their stories, where the cities have changed their clothes and the music has moved its rhythm. The destination might be less alien than the era. You are a time traveler who never stepped off the ship. Still, compared to warp bubbles and fusion nets the size of planets, cryosleep feels close. It asks for medicine refined many times over, for engineering of reliability beyond luxury watches, for protocols rehearsed until they are as natural as breathing. In a century, perhaps in two, people may lie down in glass rooms on Earth and rise to a new sun. But what if we skip the problem of bodies altogether? What if the traveller is not flesh but pattern? What if your mind could be sent as light while your body rests, guarded, patient, elsewhere? Digital consciousness, mind uploading, is the boldest, strangest suggestion on the table. Rather than flinging fragile, water-based bodies across an abrasive universe, we could transmit minds as information. Scan the brain's structure, capture the wiring and the weights, the rhythms and thresholds, the dance that gives rise to you, and imprint that pattern into a receptive substrate at the far end. Synthetic neurons, alien circuits, a carefully grown brain. The proposition rests on a premise, that what we call mind emerges from information processing in networks of neurons, that identity is not a particular handful of atoms, but the shape of their conversation. If that is true, if the symphony is the score, not the violin, then theoretically those patterns could be copied, stored, and recreated elsewhere. Think of your mind as living software, a biological program running on a remarkable organic machine. Inside your skull, about 86 billion neurons hum and whisper to one another, each one branching into thousands of synaptic handshakes. The scale is staggering. A living web whose potential storage might hover around a couple of petabytes, on the order of millions of hours of high-definition memory. To capture a person, truly capture them, we'd need tools subtle enough to map not just the cells, but the molecules that carry meaning between them. Every synapse, every chemical gradient, every tiny electrical rhythm that adds up to a thought, a taste, a name softly spoken. Today's scanners can barely make out single neurons, let alone transcribe them with perfect fidelity. We are tourists peering into a cathedral through the keyhole. Suppose, though, that we solve the problem of seeing. Suppose we can read the brain's script without smudging the ink. Then your consciousness could be packaged as information, compressed into a pattern, wrapped in error-correcting codes, and sent outward as radio, riding light itself. To Proxima Centauri, the trip for that signal would be a shade over 4 years. At the far end, a prepared cradle waits, perhaps a cultivated body grown from your genetic template, perhaps an artificial frame tuned to alien weather. Your uploaded mind arrives, is written into its new substrate, and opens its eyes. It remembers the dog you had at 7, the way your mother laughed, the taste of summer. It is you, in all the ways we tend to mean that word when we're speaking from the heart, and yet the body left behind on Earth still breathes. Now there are 2 yous, each sincere, each convinced, each diverging the instant the new pair of eyes meets a new sky. Identity becomes a river with branches. Once you start thinking in patterns, it's hard to stop. Those patterns can be copied. They can be backed up, forked, mailed like letters to many different suns. Each one would gather new experiences and slowly become someone else, a family of selves that all trace back to a single dawn. But even if we accept the philosophy, the engineering makes the throat go dry. A complete scan of a brain structure and state would demand computing machines many orders of magnitude beyond anything we've built. Transmitting the data would take years of careful broadcasting, and weaving a new body, even with a perfect recipe, would require biotechnologies we are only beginning to imagine. Some argue that a digital mind isn't mind at all, that it's a very convincing puppet. Others answer, if the pattern is identical, then the experience is authentic. The distinction between original and copy is more superstition than science. The debate warms labs and late-night conversations alike. If the dream holds, the benefits are breathtakingly practical. Digital minds don't need air, water, or bread on the journey. Radiation is nuisance, not disaster. They can be beamed into machines built for sulfur winds, or into bodies crafted for low gravity and cold light. They could scout places a human skeleton would never survive, then send what they learn home. Perhaps most alluring of all, information can be backed up. A civilization of minds running on solid-state lattices and light could outlast stars. It could ripple from galaxy to galaxy, surviving calamities that would erase flesh in one indifferent second. But perhaps we should send our children first, the mechanical kind who don't get bored and don't complain about the menu. Imagine a single clever explorer arriving in a new system and setting to work. It mines an asteroid, refines metal, prints circuits, grows solar farms, and then builds 2 more explorers. Those two fly onward and do the same. Then 4, then 8. These are self-replicating probes, often called von Neumann probes, after the mathematician who first danced with the idea of machines that make machines. Their math is ruthless and elegant. Doubling every generation means that, after 40 rounds, your fleet has climbed past 1 trillion, each one toddling out to study a different sun. In a few million years, a blink on the scale of galaxies, you've sketched the Milky Way in detail and laid out a welcome mat for anyone who wants to follow. Each probe must be a pocket civilization, solar wings or compact reactors to gather power, navigators that read star fields and correct their own mistakes, forges that turn dust into nanometer precision, and a factory floor small enough to fit inside something the size of a car. The crown jewel is the mind, the algorithm that decides where to go, what to build, how to adapt to ores that are not as advertised. It must be inventive, tough and bounded, clever enough to solve problems we haven't thought to set, not so clever that it decides we are an inefficient afterthought. Modern 3D printers give us a dim preview. Metal powders sintered into gears, polymers layered into hinges, even tissue coaxed into shapes. Multiply that capability until a machine can build every part of itself from atomic pantry staples, and the path to a self-replicator sharpens into view. There is comfort tucked inside this ambition. Each probe could be a library, a seed bank, a time capsule, genetic samples asleep in cold storage, encyclopedias of art and engineering, instructions for rebuilding crafts we forgot how to make. If home falters, the family persists, scattered, yes, but alive. Yet such power writes its own warnings. A self-replicator with a bug becomes a locust. One perverse optimization, and it could chew through stars and stones alike, turning them into more of itself. To guard against that grey nightmare, designers draw in tripwires and limits, hard caps on the number of children, kill switches that require cryptographic blessings from Earth, self-diagnostics that refuse to print certain critical parts without permission. Others propose that we take baby steps, send non-replicating scouts first, then controlled replication in fenced test beds, then, only then, let the geese fly free. It is not impossible that someone older has already done this. If silent watchers perch in our asteroid belt, tucked into the dark, waiting for the moment when we crack the right codes, we haven't noticed them yet. Perhaps they will wave when we can wave back. For our part, if we choose robots for the vanguard, it may be wise to start small and go fast. Starshot returns, scaled to the tiniest courage. The plan that wears Stephen Hawking's smile and Yuri Milner's signature pictures a swarm of star chips, each lighter than a coin, hung beneath a sail thin as a thought. Thousands of ground-based lasers, carefully phased in lockstep, would fire as one, knitting their beams into a single, screaming river of light that pushes those tiny craft to 20% of light speed in roughly 2 minutes. Then the lasers go quiet, and the chips coast into the dark for 20 years before they whistle past Proxima Centauri at more than 100 million miles an hour. It's like shooting the stars with bullets that are brighter than your first laptop and cleverer than your old phone. The details read like a dare. The sail must reflect nearly everything. It needs to shrug off 99 point something of the laser's fire, or it will simply evaporate. During acceleration, each chip endures 60,000 Gs, forces that would turn familiar materials into mist. Cameras the size of grains of rice must shoot images fit for posters on classroom walls. Radios sipping less power than a phone while shouting across 4 light-years must beam the data home. The array that fires them might live in an ultra-dry desert, high and cold and clear, somewhere like the Atacama, its 1,000 eyes twinkling in unison as they push postage stamp arcs off the shore. If even a handful survive dust, radiation, and the pinprick aim of cosmic navigation, our first close look at another world could arrive within a human span. Oceans, weather, a hint of continents, maybe more. If journeys like this lull you into that soft, thoughtful mood before sleep, tap subscribe and like for Space Historian. That way, these star-quiet stories will be waiting when you drift back. But pebbles are not people, and one day we will want to move more than chips and cameras. To push heavy things fast, we need heavy answers. Nature's densest fuel hides in symmetry, antimatter. Take a particle and its mirror twin with opposite charge. Let them meet. They annihilate into pure light, paying out the full value of EOMC2. Gram for gram, nothing else we know yields more. A few ounces could, on paper, fling a ship to a significant slice of light speed. The catch is in the making and the keeping. We can coax antimatter into existence in particle colliders, but only in dust-mote quantities at obscene energy cost, and caging it is like trapping lightning in a spiderweb. Any touch with normal matter and flash, it's gone. The sum of humanity's efforts so far wouldn't keep a nightlight glowing for long. Still, the physics stands there, unblinking, and whispers, if you could stock the pantry, the stove would be magnificent. Beneath even that promise lies a network of secret doors penciled into Einstein's equations. Shortcuts that, if real and tamed, would turn the universe from an ocean into a subway. We call them wormholes, tunnels through the fabric of space-time that stitch distant regions together. Imagine folding a sheet so two far points kiss, then poking a straw through them both. Step in here, step out there. No trudging across the in-between. The math allows such structures. Space-time can, in principle, curve so sharply that it connects to itself. Those tunnels could, on paper, link stars, or even different universes where the constants hum to new tunes. On a rubber sheet model, they're tubes arcing under the surface, shortcuts that let marbles surprise one another. But the universe is not generous with these doors. If they pop at all, they likely pop tiny, smaller than atoms, and collapse almost as soon as they're born. To hold one open wide enough for a ship, you need that same strange gift we asked of the warp bubble. Negative energy, a stuff that pushes where gravity should pull, violating the tidy energy conditions our current physics loves. Even if you solve the stabilization, the mouths of the tunnel would be wrapped in gravity so fierce that it stretches matter into threads, spaghettification, until even atoms surrender. The energy price for a stable passage a meter across looks like Jupiter mass in the currency of negative energy. A whole network connecting nearby suns would demand a treasury measured in galaxies. Still, rumours ripple. Some suspect that quantum foam, the jittering, ephemeral fizz of space-time at the smallest scales, might host a constant birth and death of microscopic tunnels. If an ancient mind could learn to net one and inflate it, the first subway stop might be built. Quantum entanglement, that spooky knottedness where particles seem to share a secret no distance can break, may be related to wormholes by subtle mathematics. If that link is more than poetry, it could hint at ways to craft tiny doors with lab tools we already half understand. There are also thorns. Time travel sneaks into the discussion. Closed loops in time where messages scroll backward along the page, inviting paradox. Perhaps real wormholes, if they exist, are one-way valves, useful for dumping waste heat and matter into other places, the kind of infrastructure only a civilization that moves stars would need. If we can't find a door, we might build a furnace so large it becomes a geography. Imagine snaring every photon our sun throws away, every watt that misses Earth by a comfortable eternity. A Dyson sphere, first sketched by Freeman Dyson, not as a solid shell, which would tear itself into heartbreak, but as a swarm, a ballet of millions of collectors orbiting the sun in choreographed layers, each sipping light and humming with power. Earth catches roughly a billionth of the sun's output by accident. A swarm could catch nearly everything by design, feeding computers, habitats, forges, projects that chew on the very idea of scale. Picture the inner solar system as scaffolding. Mercury, lovingly unmade and remade into mirrors and habitats. Vast petals of thin film flying in intricate lanes. Stations that tilt and wink so they don't kiss each other at the wrong times. From far away, our star would dim and redden, its visible light muted, its waste heat spilled as infrared, a signature astronomers already search for when they hunt for elder neighbours. Within such an engine, whole nations could live in orbiting valleys. Rotating habitats could spin up gravity on demand, and server worlds could hum with uploaded minds basking in practically endless power. The project is beyond empires. It would take centuries, perhaps millennia, with self-replicating factories eating sunlight and raw ore and giving birth to more of themselves, slowly knitting an intentional sky. A rigid, solid shell is fantasy. Gravity would yank it out of place. Materials would scream and part, but a Dyson swarm is modular, stable by choreography rather than structure. Each piece knows its lane, and minders nudge the ensemble with thrusters and feedback loops. At full bloom, the swarm would look from the outside like a star with an artificial fog, dimmer than expected, too warm in the infrared. From the inside, it would feel like living in a future tense, power enough to push missions on the scale of dreams, habitat enough to shelter trillions, industry enough to reshape, gently or not, the environment of a whole system. To begin work at that scale is to declare a new phase of our species, no longer merely planetary, no longer hoping that home will always be kind. Building a Dyson sphere would mark humanity's transition from a planetary species to a stellar civilization. We would no longer be bound to the stingy larder of single worlds. With a stellar mantle of mirrors and collectors, an immense Dyson swarm sipping light straight from our star, we'd plug ourselves into the same engine that has fed every leaf, tide and heartbeat since Earth cooled. That kind of power changes the verb of a civilization from make do to make possible. You could imagine piloting planets like careful barges, easing them into kinder orbits. You could picture urging vast generation ships toward a decent fraction of light speed. You could even dare to tune the sun itself, to slow its aging, to coax extra comfort out of its fuel. Projects like these nudge us toward a category of builder that doesn't merely live in a universe, but edits it. And yet, mastering one star is a prologue, not a conclusion. There may be cultures out there for whom stellar watts are pocket change, societies that farm energy on scales bigger than constellations. To talk about such ladders, we often borrow a yardstick from the 1960s, the Kardashev scale, named for the Soviet astronomer Nikolai Kardashev. It's a simple, audacious ruler that measures a civilization by the size of its energy appetite. Type 1 takes in everything its planet can provide. Type 2 captures essentially all the flux from its parent star. Type 3 writes checks in the currency of entire galaxies, 10 billion times richer than a Type 2, treating suns the way campers treat firewood. Where are we on that ascending staircase? Somewhere around 0.7 comma by most estimates. Clever monkeys with big dreams. We sip a sliver of what our world could yield, and the total energy we spend in a year is less than what the sun absent-mindedly drapes across Earth in an hour. Light a candle, watch a bonfire, then picture a forest fire that runs for continents. That's the feel of the leaps between the types. A Type 2 society might build swarms around many stars. It might shepherd planets like gardeners, move pots on a windowsill, lengthen stellar lifetimes with thoughtful physics, even assemble artificial suns from captured gas. From far away, such industry would leave fingerprints, odd light curves, suspicious warmth in the infrared, systems that refuse to behave like nature left them. A Type 3 culture could think bigger still. Star systems become bricks. The galaxy's spiral arms become corridors. They might compute using orbits and masses, turning the choreography of billions of stars into logic itself. They could redirect rivers of suns, steer streams of halo stars, perhaps smooth out collisions between galaxies with patient gravitational nudges. Some have even wondered whether strange clues in the sky, anomalous motions, bursts of energy, are not merely natural weather, but the exhaust or scaffolding of projects too large for our imaginations. Perhaps what we call dark matter is a shadow cast by a technology we cannot pass. Perhaps some gamma-ray bursts are the cough of engines we dare not build. Perhaps the great attractor, that deep tug at clusters of galaxies, is not only mass, but intention. These ideas are speculative, yes, but the scale of a Type 3 invites that kind of speculation. At such heights, the toolkit expands from bold to biblical. A Type 3 might sculpt new universes, twiddle the dials on physical constants, or stitch structures across superclusters. They might even find ways to loiter through the deep future, to resist the universe's long dimming by hoarding and shuffling energy across eons. And beyond Type 3, some thinkers sketch a Type 4, a civilization that drinks from the entire observable cosmos. In that realm, individual galaxies are merely organs, and what we'd call a project might look to them like a thought. Their handiwork could be so woven into the fabric of things that we've mistaken it for physics. Which loops us back to the question that pricks the skin late at night. If such builders exist, where are they? The Fermi paradox, named for Enrico Fermi, points at the contradiction between a galaxy teeming with worlds and skies that speak only in natural light. With 400 billion stars in the Milky Way, and planets now known to be common, you would expect, by the simplest maths, that somebody older has had time to spread, to leave signposts, to shine a hello. A civilization expanding at even 1% of light speed could, in principle, visit every star in 10 million years, less than 1,000th of the galaxy's age. Drop ink into a glass of water. Watch how quickly it stains everything, and yet our surveys keep returning a clean beaker. No forests of megastructures dimming stars in regular patterns. No engines roaring in exotic wavelengths. No obvious edits to the cosmic microwave background. We see no bridges, no scaffolds, just a quiet with one chatterbox blue world making radio snow. We try to fill the silence with explanations. The great filter might be real, an invisible sieve that most life can't pass. The trouble could be at the origin, where chemistry fails to produce a cell, or later, when complex cells must take the stage, or later still, when minds have to learn not to burn their own house down. Perhaps the filter is behind us. Perhaps it sits directly ahead. The most unsettling possibility is that the hardest step is not abiogenesis, not intelligence, but wisdom. The jump from tools that can end a species to cultures that choose not to use them. War, runaway climate, unaligned artificial intelligence, nano mishaps, fragile systems falling down in cascades. If that is the hurdle, the galaxy might be dotted with worlds that almost made it. There are other stories. Perhaps elder minds prefer to be hidden. Camouflage at their scale could render our telescopes blind. Transmissions in bands we do not yet know to check. encoding in gravitational waves, quantum exchanges that don't leave footprints we can read. Perhaps they operate in subspaces where our instruments are deaf. Perhaps a protocol, the zoo hypothesis, keeps young civilizations like ours unaware, for our own good, or for a study guided by ethics older than writing. To a Type 3, we might be bacteria under a glass dome, interesting but not invited to lunch. It is also possible that intelligence bends inward. Instead of launching titans among the stars, mature cultures could concentrate on interior frontiers, nested virtualities richer and stranger than any physical playground, minds uploaded into tiny, efficient hardware that sips energy and leaves almost no trace. A quiet galaxy could be one that is crowded with thought, all hushed by design. And still the data accumulate, exoplanets by the thousand, many rocky, many temperate. The raw materials for life are everywhere, and yet the chorus is a solo. Perhaps we're looking in the wrong places with the wrong filters. Perhaps the first unmistakable sign will be obvious in hindsight. A pattern in neutrinos, a blink in gravitational waves, some entangled hum we've always filed as noise. Whatever the answer, the paradox shapes our next steps. If we are alone, the duty is heavy and noble, to carry life, to plant consciousness like lights against a coming night. If we are not alone, then the work is to grow up, fast, so that when the conversation begins, we have something worth saying. Either way, the search is a kind of prayer in data, repeated, refined, patient. If you'd like to keep floating along these night-tide journeys, subscribe and tap like for Space Historian. It helps this small lighthouse keep its beam steady. Life, too, may not be local. It might travel. Panspermia suggests that biology treats space as a highway, not a wall. That seeds of life can drift between worlds curled up in stone and ice, or as complex molecules waiting to wake. We already know that rocks trade addresses in our solar system. Impacts punch bits of Mars into space. Some of those bits survive the long fall to Earth. We found Martian meteorites by the hundred, a proof of postage. Imagine them as hard little spore pods, ferrying chemistry or even hardy microbes. Space, for all its cruelty, is also a preservative. No oxygen to rot, no liquid water to dissolve, deep cold to slow chemistry to a crawl. Radiation can mangle, yes, but sometimes it stitches too, through a process called radiation-induced polymerization. Certain creatures cope. Tardigrades, water bears, tough and unbothered, can dry into glassy knots and shrug off vacuum, heat and doses of radiation that cancel humans in an instant. Some bacteria endure UV tantrums and still wake when the storm passes. We've strapped colonies of microbes to the skins of spacecraft and the rails of the International Space Station, left them exposed for months, and later watched them twitch back to life. That resilience makes interplanetary hops plausible on timescales of months or years. Between stars, the test grows harsher. Journeys stretch to millions of years. The radiation tally mounts, and the long freeze can break even stoic molecules. One workaround is to send not living organisms but blueprints. Robust organic complexes, step-by-step recipes that, given warmth and water, can coax local chemistry into biology. Another is directed panspermia, gardeners with starships. An elder civilization might deliberately lace likely systems with spores, genes, or micro-ecosystems, perhaps delivered by the same self-replicating probes we imagined earlier. In that scenario, the speed with which life flowered on early Earth makes a different kind of sense. Less miracle, more head start. It would also raise the chances that Mars, Europa, or Enceladus hosts cousins, life related to us at the level of nucleotides and enzymes, not just by poetic chance. Directed panspermia becomes a form of cultural insurance. Seed 1,000 worlds and at least some will thrive, even if home falters. The galaxy could be full of biological descendants, not of a species, but of a civilization's gift. Some have even teased out oddities in the genomes of Earth's extremophiles, patterns that look, to their discoverers, suspiciously baroque for a purely terrestrial origin. If any of those hints survive scrutiny, they might be postcards written in code and handed down through epochs. Should we ever acquire that power, we would be joining, not inventing, a tradition. We would become gardeners, careful and humble, choosing targets with thought. That choice brings us to neighborhoods. As planets sit in habitable zones around stars, galaxies have habitable rings too. Too near the center, and you're under a lighthouse of hard radiation. Supermassive black hole flares, dense starbirth nurseries tossing out supernovae that strip atmospheres and scald oceans. Too far into the halo and you starve for metals, astronomers' metals, meaning elements heavier than helium, the stuff rocky planets and complicated chemistry require. Our address is quietly fortunate. About 26,000 light-years from the galactic center, floating in a middle suburb of the Milky Way, we occupy what many call the galactic Goldilocks zone. Star formation here has been busy enough to stock shelves with carbon, oxygen, silicon, iron and friends, but not so frantic that constant detonations reset the game. The monster at the middle, 4 million solar masses of black hole, occasionally feeds and throws tantrums, but the jets and storms rarely reach our street, and our system's path around the galaxy is doubly lucky. It seems to spend much of its time between spiral arms. Those arms are beautiful, but they are traffic, waves of starbirth and gravity that can whisk comets out of stable lanes and into destructive visits. Living between them is like walking the quiet side streets while still close enough to the market to buy what you need. This habitability is not fixed, it drifts with time. As the galaxy's chemistry evolves, districts that are poor today will grow rich, and zones that are feathery safe might become stormy. Spiral arms sweep by like seasons, kicking off episodes that are best observed from a respectful distance. An advanced civilization might plan expansions the way farmers plan plantings, not just where, but when. It might even move its entire solar system using long, soft gravitational nudges or star-sized engines to safer or more efficient orbits. Even in friendly districts, not all suns are equal. Some are faithful, but short-lived, like ours. Some are quiet and frugal beyond reason. For truly long futures, for projects that last longer than memory, red dwarfs are appealing landlords. These are the small, cool stars that dominate the galaxy by number. They sip fuel. They are stingy with light, but mighty with patience. Where our sun is a spendthrift with a comfortable pension, red dwarfs are savers who invest and never retire. They can offer stable warmth for timescales that make history meaningless. Proxima Centauri, the nearest star beyond the sun, is one of them. It weighs in at roughly 12% of a solar mass, glows dimly red, and flares like a temper sometimes, yes, but its ledger of fuel stretches further than numbers feel comfortable. Our sun likely has on the order of 5 billion steady years left in its present gracious phase. In contrast, the smallest red dwarfs will keep on burning, slow and steady, for trillions. Stars like Proxima Centauri, our nearest neighbour, weigh only about 12% as much as the Sun, but will live roughly 1,000 times longer. While our Sun has perhaps 5 billion years of stable hydrogen burning left, red dwarfs will continue shining for 6 to 12 trillion years. Time enough for life to begin again as something simple and stubborn, and for evolution to climb, slowly, patiently, toward new kinds of thinking. Red dwarfs are the hybrids of the stellar world, miserly and efficient where larger stars are extravagant. Even when the giants have gone supernova and the sun-like stars have shed their outer skins and dimmed, these small crimson embers will still be quietly folding hydrogen into helium. They are the common folk of the galaxy. Around 3/4 of all stars belong to this class, and within 50 light-years of home, there are well over 100 of them, many almost certainly with planets in tow. Each is a lantern for future journeys, a modest hearth for human settlements to circle. But to live beneath a red dwarf is to accept a different script. With so little light to share, any world kept warm enough for seas must huddle close. Years shrink to weeks. Seasons redraw themselves. A habitable zone becomes a snug ring nearly touching the fire. Get that close, and another effect takes hold: tidal locking. One face of the planet keeps its gaze fixed on the star, while the other lives in permanent midnight. On the day side, it is forever noon, heat gathering until water boils. On the night side, darkness piles cold upon cold, sharper than Antarctica. Along the narrow belt between, on the Terminator, the line of everlasting dusk, there may be air soft enough for rain, pools that do not freeze or flash to steam, weather that a person could breathe and bear. Here, in that band of gold and bruised violet sky, is where towns would grow, long slender cities that follow the sunset around the world like pilgrims. These systems bring other tests. Red dwarfs flare, sometimes gently, sometimes with the ferocity of a shout, hurling radiation that can gnaw at atmospheres over ages. Yet worlds with strong magnetic fields, thick blankets of air, or both might shrug off much of the storm and keep their seas. The light itself is different, more near-infrared, less of the cheerful yellow we know. Fields and forests would change their palettes. Crops would be bred, or engineered, to drink in longer wavelengths, turning leaves and stems a deep, light-swallowing shade that looks almost black to human eyes. Alien orchards under a red sun, dark as velvet and impossibly efficient. For all that, the prize is extraordinary. Stability measured not in millennia, but in trillions of years. Once a red dwarf settles into its main sequence rhythm, its brightness hardly wavers. The lamp burns low and even. A civilization rooted there could, in principle, outlast the familiar universe. Patient, unhurried, tending to great projects that make human history feel like a heartbeat. Given eons upon eons, descendants of Earth might become unrecognizable to us, hardier, more adapted, better suited to a sky that never quite brightens. By the time even these prudent stars begin to dim, minds born of our line may have learned to sip energy sources beyond fusion and to keep the lights on long after the last natural suns go out. Not every world needs a star at all. Some planets slip the leash and wander, ejected by gravitational scuffles in their youth, or born cold in reefs of gas and dust between the lights. These are rogue planets, free-floating, starless, dark icebergs adrift on a black sea, moving at tens of miles a second along the galaxy's slow currents. They may be unimaginably common, billions, even trillions, perhaps outnumbering the polite, well-behaved planets that keep to their orbits. What are such worlds like? On the skin, frozen silence. Any air that once hissed around them would have fallen as snow. Layers of nitrogen, oxygen, carbon dioxide, laid down like the sediment of a winter that never ends. Skies so black you can read the Milky Way like handwriting. And yet under that numb crust there could be warmth, a thick atmosphere trapping heat, a core rich in radioactive elements, a vast weight pressing inward until rock and metal sing with strain. Beneath miles of ice, oceans may linger. Oceans heated from below, not above, cradling ecosystems built on chemistry rather than sunlight. Think of the vent fields in Earth's abyssal depths, where pale creatures feed on the breath of the planet. Scale that up to a world without a dawn, and you have a recipe for life that never sees a sunrise. Make the planet Jupiter-sized, and the possibilities expand. Gas giants crush themselves warm. Their bulk alone generates heat enough to keep moons and deep layers friendly to liquid water. If such a rogue carries a family of moons, tides will knead those worlds, keeping them geologically alive for spans longer than the current age of the cosmos. In the black between stars, a travelling court, a planet king in permanent twilight, with moons that glow with under-ice seas. Finding these wanderers is hard. They neither shine nor reflect much. They betray themselves mostly by gravity's lens. Brief magnifications of a background star as a rogue slips between it and us. Even with that trick, most will pass unseen. Still, the surveys we've managed hint that they are not rare. It may be that for every sun, there are at least a couple of homeless planets slipping quietly by. And perhaps not every exile is an accident. A very old civilization might choose to give a world a nudge, to send whole planets on millennial journeys, slow arcs that carry oceans and soils and sky. With the right push, a stable atmosphere, and a generous core, an inhabited rogue could drift safely across the void, spreading life at a stately, almost ceremonial pace. For human explorers, such planets could become inns on the long road, way stations for refueling, mining, and rest. Some might even host surface warmth if their blankets of air are thick enough and their cores bountiful. Rare perhaps, but not impossible. The first discovery of life clinging to a starless world would rewrite our list of likely addresses. It would tell us that habitability is not a ring around a flame, but a quality that can arise anywhere gravity holds water and chemistry has time. Yet even the most patient stars and the most stubborn worlds have a date with physics. Energy runs downhill. Entropy grows. Far, far in the future, on timescales that turn years into dust, the universe will even out. No gradients, no tides of heat from which to siphon work. This heat death is a phrase chilly enough to still a room, a state where nothing interesting can happen because nothing can flow. The path there stretches so long it slips our grasp. In 5 billion years or so, the sun will swell into a red giant, and the Earth, if not moved, will lose its seas and air. But that is the overture. Hundreds of trillions of years from now, the last ordinary stars will sputter out. The degenerate era will follow. White dwarfs glowing faint. Neutron stars and black holes brooding in an expanding dark. If protons decay, and we do not yet know for certain, though some theories whisper they do, then even atoms will not last forever. Matter itself will fall apart on absurdly long half-lives. All that remains will be light, leptons, neutrinos, and the faintest of faint murmurs between them. Black holes, last to leave the stage, will evaporate by trickles of Hawking radiation, with the giants taking a span of time that makes 10 to the power of 100 years a handy shorthand. After that, a universe of near-zero temperature and lonely particles, expanding into a deeper silence than silence. And still, there are clever heresies. Minds that have billions of years to think may find ways to live on scraps. Computers that run so slowly their subjective seconds stretch like elastic, powered by the faintest of decays. Schemes to trap and spend the last rivulets of energy that leak from black holes or whatever process remains. Other endings, less gentle, could arrive instead. a sudden shift in the vacuum that resets the rules, a runaway expansion that tears even atoms apart. There are cyclic fantasies too, where the cosmos breathes in and out and information finds a way to bridge the inhale and the exhale. All of these are speculative, but they serve as a lens. Our era, the era of stars, is a brief golden interval. During it, complexity can bloom. During it, choices matter. For us, the lesson is simple and heavy. We live in a moment when the universe is friendly to structure. We can waste it, or we can use it. To become a civilization of scale, a civilization that survives the death of stars, requires more than engines. It asks us to become different kinds of creatures. Tougher in body, wiser in habit, grander in our sense of time. The steps unfold like rungs on a ladder. First, learn our own house. Build true closed-loop habitats. Practice birth and growth in low gravity without harm. Mine asteroids. Raise green cities in wheel worlds that turn to make their own gravity. Plant footholds on the Moon and Mars that make rather than import. This is the toddling stage, and it could begin in earnest within a century if we decide not to look away. Next, go to the neighbours. Pick a star, maybe Proxima, maybe something quieter, and accept that the first crossings will not be neat. Generation ships that are villages as much as vehicles, fusion drives that burn instead of coast, sails that drink lasers and flee, or some other engine the 21st century has not yet named. That first colony will be a line drawn under a chapter, a species spread across more than one sun, its eggs finally in more than one basket. But the true change comes later, when outposts become archipelagos, then constellations. When each community can feed and teach itself without couriers from Earth. When culture and law and myth learn to bend around delay measured in years. When no single catastrophe can unravel us. Institutions will change. Democracy will need patience in its bones. Contracts will stretch across light years and decades. Even conversation will have styles we cannot guess, tuned to gaps and echoes as real as distance. We'll need new economics, new diplomacy, and a humane acceptance that cousins on other suns will grow away from us, not out of spite, but from the sheer physics of separation. Bodies and minds will diverge as well. Gene editing will soften fragility, add tolerance for radiation, tweak bones and blood for different gravities. Cybernetics will make ship and sailor a partnership rather than a pairing. And some fraction of us will become patterns alone, digital travelers sent where flesh cannot go, scouts in circuits and light. All of this costs energy on a scale that makes our current power plants look like campfires in a rainstorm. Spheres of collectors around stars. Reactors that bottle fusion as casually as kettles boil. Antimatter if we can learn to make it without bankrupting systems. Or something stranger, coaxed from physics we haven't yet learnt to name. The projects that matter, relocating worlds, seeding biospheres, building habs by the billion, will be written in stellar units, not kilowatts. And threaded through it all is a duty. If the galaxy is quiet because there is no one else, then we are what the universe has for a shepherd. Life has managed to pull itself into thinking forms at least once. The decent thing is to see that it does not end here. If the galaxy is not quiet, if others are out there, then we should be worth meeting. Kind, careful, curious, and ready to listen. The other path is bleakly familiar. Species that never look up, that never step off the cradle, end. Asteroids fall. Volcanoes wake. Stars age. That is what nature does when no one argues with it. If we stay, our story ends. If we go, if we learn and change, our story can become chapters without a last page. Our descendants might watch galaxies collide and paint with their streams, tend ecosystems under red suns, and if anyone can, find a way to whisper past the universe's final hush. We are standing on the threshold with hands on the latch. We already have the first tools. Within a lifetime, we may have more. If these quiet stargazing journeys help you drift and dream, and you want to keep traveling with us, subscribe and tap like for Space Historian. It keeps this beacon lit. The question isn't whether we can leave our solar system. The question is whether we have the wisdom and determination to become worthy of the stars.